This might be the worst vacuum ever. And pun intended, it just sucks. And unfortunately, not in the literal sense. But in this abomination of a creation, I was able to record some data, look at some results, and try to analyze why it sucks, figuratively speaking, and see if I can learn something. So let's get started. At the heart of this vacuum is a 35 watt DC motor with a max RPM of 3000, which we will later come to find is one of the biggest constraints. And for the design of the blower, I tried to go for a centrifugal design where air is sucked through the center and pushed out the sides tangentially. For the impellers, having never designed one before, I thought it'd be interesting to print a couple different types out and test them out to see which one performs the best. With the first style being a radial impeller that are just straight blades that go from the center out to the edges. For the body, we basically need a bucket with a place for the nozzle to attach to. And while this bucket mostly turned out, the print kind of failed at the top, which is why the surface is a little rough. But a bucket is a bucket, and this will do. For the lid, all it needs to do is cover the bucket, have an air intake hole, and some bolt holes to attach the blower to. Putting it all together, we're almost ready to go, except for one electrical fitting in order to connect the power to. Plugging it in, it's apparent that the rotors aren't quite balanced since there's quite a few vibrations. And pushing the lid down, it seems like we could quiet the vibrations if we clamp the lid down. Now it's clear that it can blow, but the question is, can it suck? And the answer to that question is not really. With the fine paper scraps, it struggles to get up the tube and into the bucket. And if we up the size of the paper scraps, even though it's still lightweight paper, it can't suck it up at all. And so the follow-up question to this is, can we play around with the design a bit and see if we can do something about the lack of static pressure? And to measure the change in static pressure, I put together a crude manometer that looks at the change in fluid height in order to compute it using this equation. Rho is the density of the fluid in our tube, g is the acceleration due to gravity, and delta h is the change in fluid height. And if there's no measurable change in static pressure, we can use our ammeter in order to compute the power and see which design's more efficient. Here, we'll multiply the current by a constant 12 volts by our power supply. Starting with the radial blades, it becomes quite apparent why we can't suck anything based on the minuscule static pressure we're reading. Power-wise, we seem to be drawing around 0.4 amps. And measuring the delta H, we'll record 4.69 millimeters. Next up are some curved blades that are curved against the direction of the motor spin. Turning it on, it's hard to see, but when I got level with it, it appeared to be just a hair bit taller than before. But there definitely seemed to be a noticeable reduction in current draw, at around 0.382 amps. Measuring the delta H, it seemed to be just a little bit taller, at around 5.17 millimeters. Next up, I wanted to see if increasing the blade height would help, so I made a larger casing, and a correspondingly larger curved blade. Turning it on, it definitely sounded worse, and there didn't seem to be much of a change compared to the radial blades. And current draw-wise, it seemed to be the highest, at around 0.406. Looking at all the results, the clear winners seem to be the curved blades at the lower impeller height. And considering how much headroom there is power-wise, it's a 35 watt motor, I wonder if I could have used a larger diameter blade versus a larger height on the blade to push more airflow and perhaps bring the static pressure up. For comparison, I have a 4 horsepower shop vac, And right off the bat, I can tell it's definitely a lot louder, but it's also definitely a lot more powerful. Since there was more static pressure than I can measure, I looked it up online. It's about 200x what we were able to create. But if our blade design didn't seem to have the biggest impact on our performance, what parameter would? And for that, I turned to the fan affinity laws. And what stuck out to me was how RPM was proportional to the square of static pressure and to the cube of power. What this means for an identical design, keeping the same fan geometry, if we were to double x the motor speed, we would see a 4x in static pressure. And conversely, if we were to double the motor speed, we would see an 8x in power draw. Comparing our motor to what's used in some other vacuums, we're about 8x slower than what's typical. Power-wise, our 5-watt peak power draw is about 200 times less than the peak power draw of our shop vac, which is interesting since we're also about 200 times weaker pressure-wise. In summary, if we wanted to suck less figuratively and suck more literally, the biggest thing we could do is get a faster motor. Other things would include a better seal on the housing, balancing the impeller which would give us less vibrations, and considering the headroom on power, if we were to keep the current motor, it would probably be beneficial to increase the diameter of our impeller. With all that said, I certainly had fun playing around with perhaps the world's suckiest vacuum, and definitely got to learn something. Thank you for watching.